wait a few more minutes, maybe a few more people come. I'll start, say, in 2 or something minutes. Okay, we can start. All right, so my talk here is about, and please feel free to ask questions. We are a small group, and I have prepared the talk. There are too many topics in there, so I will skip over things. I will talk about things when there's interest, and skip things that are less important, and so you can basically have a say what you're interested in. So essentially, the general topic is about information flows in the perception action loop. And I will explain exactly what that means. And perception action means basically agency. We're thinking of agents here. Just for those who don't know where the University of Hertfordshire is, it's in the United Kingdom, just north of London, on the way from London to Cambridge. And sometimes people say Hertfordshire. No, it's Hertfordshire. If you forget how to say, just sneeze. Okay, so there's a big list of people that are involved in the things in this research. It's not a one-person show. It's actually a lot of effort from a lot of people, colleagues, friends, and PhD students. Okay, and these are the people who paid for part of that. And here is a quote from Oscar Wilde, which I think he would have enjoyed our modern social media a lot. It is a very sad thing that nowadays there's so little useless information. I think that's such an amazing quote. Okay, so let us start with a basic model that I'm going to consider. And we begin with the simplest of all models, an unstructured Markov chain. So we write basically W is the world at different times, W at time t minus 3, t minus 2, t minus 1, and so on, and the arrows indicate a conditional probability in the sense that given this, I have a probability on W, and when I have a node without an add parent, it's just the probability a priori given. And here I don't need it yet, but I will imply that every such arrow is a causal mechanism. So in other words, with such a network comes semantics. What happens if I intervene? Right, so if I intervene in a node, everything downstream is going to change. This is going not to be so important in the Markov chain, but it's important when I start talking about agents. Now, let's add an agent. What is an agent? So we have here a blind agent. What's a blind agent? An agent is simply this action node. So we have two nodes now. For example, this one is a conditional distribution given this and given this. We say it's a blind agent, there's nothing else to, so it is implied that all these action distributions, or basically these mechanisms, are time agnostic, which means they are homogeneous in time, they are the same. Right? There's no hidden memory somewhere in the system that remembers at which time step we are, which we would have if they were different. So there's a symmetry here that all these conditional distributions are the same. And so are the A's. W, of course, does not have to be fixed. That can change over time because there's a time flow, but we consider basically a blind agent policy which constitutes simply a fixed policy A on the system. You can read that as a parameterization of the dynamics of your world. So think of an agent here as a parameterization of what the world is doing. I now close this loop by a generically sensing agent. Generically means it can, in principle, look at anything you want, right? I will later add sensors, but right now I don't. I can actually look at whatever I want, And this will be quite interesting in a second. And this is of course an agent that now reacts to the world. Again, the arrows are, there is no implied memory, so it means all the arrows do the same thing. What is not necessarily the same anymore over time is the actions, because they can change depending on the state of the world. There's nobody, I'm not talking about stationary states. Definitely not stationary, I don't require that. Next one, I introduce sensors. So I have a word, a sensor. What's the difference between a sensor and generically sensing? The sensor is constrained on what you can sense, and it changes what you're allowed to look at, and several aspects that are influenced by that. We will, right now at the beginning, not need so much to discuss sensors, but later it will make a difference. Sensors are de facto limited by physics. In other words, you cannot generically choose anything to look at. The reality is it's limited, but I will often consider the case where I don't care about the sensor. Give me just a sensor that does the job is something we are going to consider later. And the most complete model is an agent with memory. That means now we actually have memory. This is the memory, and this is a Bayesian network, causal Bayesian network. The world impinges on the sensor impinges on the memory, basically meshes it up with whatever comes from the past, creates a new action, and so goes the cycle. This is the most complete model of a discrete time agent in the world. Yes?
Isn't the memory also like kind of implied from the previous slide?
Yeah,
Like
yeah. This goes on forever.
Yeah, in the previous slide, like the agent could, I can imagine the agent like writing its memory into the world and reading it the next day, and I think that could be like a memory.
Very cheeky. Yes, this is called stigma G. You can do that, of course.
The stigma G.
Stigma G. Stigma G is what ants do.
So like typing?
Stig, like stigma, S-T-I-G, M-E-R-G, like
Okay. Stigma G.
Stigma G.
Interesting, okay.
Yeah, stigma means the signs. It's basically, you know, when Jesus appears with wounds, this is a sign that was imprinted on him. So stigma G is basically the fact that you leave signs on the ground. Well, writing is a form of stigma G, right? And anytime you actually export stuff that you should memorize, that's stigma G, strictly spoken. And you already point on something very subtle, but right now I will just do the naive thing. This is the memory in your brain. You don't really write it. Of course, if I say note to self, it's a very weird mixture of stigma G and memorizing, right? Because you pretend like the brain is a memory. But perhaps it's not that wrong. If you look at this diagram, it's very striking that actually, if I don't tell you anything, the diagram is completely symmetric with respect to the sensory action separation. And this symmetry, I don't think it's by chance. It's real, even if the world is not agentic. If it's agentic anyway, it's clear. But I don't assume it's agentic even. It's very symmetric. And the question is there something deeper? I believe there is. And the reason we distinguish agents from world, that is now complete speculation, is actually of semantic nature. It cannot be read off the syntax. It is read off by the fact that the agent can choose its memory encoding, but the world cannot. We can choose how we encode things. We can choose to speak in English, French, Italian, Italiano, or German, Deutsch. We can choose this code. There are lots of freedom. It's not arbitrary, but there are lots of freedom choosing the code. There's no freedom of choosing what actually happens in the, sorry, I went too far. What happens in the world. The world has a lot of implicit structure that can be compressed away by agents. This is a long story, but I just want to make this point. The other thing is, you should notice that we took care of making sure that M is symmetric to W when you mirror here. So that was, and we used to call it R, but then we changed it because we felt it needs to be symmetric.
What did R stand for? What did R stand for?
The rest of the world. Yeah, it was not a good choice of name, but this is better,
I
yes.
think we should rename A to I for intervention.
For intervention?
So let's get off the topic.
Yeah, I is a loaded term, and
That's-
H
oh,
is too.
That's true, isn't it?
Yeah, so we will need I. Now I want to pinpoint a high-level view on what we're going to do. I'm going to look at information in this context. Information is always implied various forms of channel information and trends, right? It's not going to be anything else, just channel information and the derived quantities. And I'm going to talk maybe a little bit about relevant information. It's the information you need to do a task. We'll talk about that a bit later. But for now, just let us suffice. Relevant information is information you need to pull in to do something. So if I want to grab this object here somewhere, blah, blah, I need to take in the information. Where is this bottle? I have to walk and so on. So we can consider that information you pull in from the sensors, process, and then use to choose your action. And we call that relevant information. If you don't have memory, so you have just a processor, we can basically just compute in every step this relevant information. And in a way, it's a pull information. It means we pull this information from the environment. This is what information we want. And where there is pull, there must be also the push, the dual question. And that is a question that people didn't look at because they thought, well, it doesn't make sense. Turns out it makes a lot of sense and you can do a lot with it. But this was not obvious at the time. And that is empowerment. I'll talk a little bit about that later. It's push information. What's push information? If I look at the information, I can push through the actuators into the world and recapture myself. This is empowerment. It's what I can do to the world and actually see that I do. Later we'll motivate what it means. For now, just believe me, it's useful, or you don't have to believe me. Maybe it's even better if you're skeptical, because it was almost a chance discovery. So let's start. What can you do with this type of stuff? Let's do something to start with. Invariance. So if you look at, for example, physics, you think of energy conservation, things like that. Turns out there are, even if you're not in the Landauer limit, right? With the Landauer limit, you can, of course, transform energy into information, vice versa. But I'm far away from the Landauer limit here. I have just an agent living in the world. And the first person to realize that information is something you can actually quantify and use to characterize what you can do. He had the statement, very informal, very ad hoc argued, but the basic idea was there. Only variety can destroy variety. So if you want to remove entropy from the environment, you have to have variability. And you have to have access to this variability. A more precise way of doing that is the extension by Touchette and Lloyd. Hugo Touchette was a master student of Seth Lloyd at MIT, and he told me that it took them 4 years to publish the full paper because the physicists thought, oh, that's not really physics, and the information theorists thought that's trivial, nobody was interested, as always, right? It's always the same game, so don't get frustrated, that's what I'm trying to say. Never give up. They ended up publishing it, and here's the main theorem that they prove. The following. Let's assume we have an open loop controller. So back to our original blind agent. Open loop means the agent has these actions, has no memory, and basically just does something. Fixed random choice of actions. But now I imagine an evolutionary process or a design, or it doesn't really matter who does it. And that evolutionary process selects this action distribution in such a way that it maximizes the entropy reduction in each step, or let's say in a particular step. Let's pick a particular step, let's say this one. The entropy reduction of this world to this, you want to, doesn't matter in which form you want to reduce it. You want just to reduce the entropy of the space, of the state, and you maximize it. So you pick an action that maximizes entropy reduction. Think of it, you have a dirty room and you maximize how much dirt you remove. And when this is maximized, let's call it delta H star for the open loop. So an agent that cannot observe what it's doing. The examples of that, for example, there are these robots that just move around back and forth, and they push stuff to the walls. This is a nice experiment. They're basically blind robots. They don't do much. And then the theorem says, if you close the controller, you close the loop, right? Then the reduction achieved by the closed loop controller cannot exceed the open loop reduction plus what you see. So that's an upper limit. Yeah, it might be less, but it will never be more. So you cannot get better than the amount of information you get from the environment. That's right, and it might be nothing at all. Why nothing? Because you could have, of course, an observation of the environment that's completely useless for the task. So you, just a second, I'll just finish the sentence. So it might be, you might be looking at a galaxy far, far away, watching Star Wars instead of cleaning your room. That is extra information, but it's completely irrelevant to the entropy reduction. Yes.
It's not stationary, so what does I don't need here AT? Like
Yeah, you here for this theorem they just look at a single step.
the delta H star open is like the entropy, like the delta is like entropy reduction over the whole thing.
No, over one step.
Ah, I see. Okay.
They look at just one step. You can do that for multi-step development, but they only look at one. I just put this whole diagram in because I'm going to talk about actual sequences of actions later. But yes, yeah, you can get a similar theorem for the big one. That doesn't change much. The interesting part is you have an invariant constraint that is informationally only, telling you how good you can do in the real world, solving a task purely in terms of information. That is, yes.
So this is a delta H, which doesn't necessarily correlate to any sort of meaningful task.
No.
But if you're,
Yes.
but you could connect it up as like if your task required entropy reduction,
Yes.
this would be that part of it at least. Yeah.
Absolutely. Absolutely. I did not talk about what the task is. I just talked about entropy. Right? And then maybe the task of interest doesn't require maximal entropy reduction either. Right? So maybe the only thing is I have this messy children's room and all I have to do is hit the darts on the board. That is not a maximal entropy reduction. Yes.
So a thing that you can do is encode a utility function as a prior, and then like you can rewrite like doing stuff, like trying to do something in the world in terms of trying to minimize the differences between the world and the prior. Does that hook up to this at all, or could it?
You probably could think of ways of getting it close to this one. It would require a bit more than that, right?
Okay.
Because this is just saying, I don't care what the entropy reduction looks like. You could try to do something like active inference and say, okay, how much can I reduce? And I guess maybe that has been done in a form or not, in a form or different form. It would have to be translated to this formalism to really be matchable. We do it differently. I'll talk later about how we do that. It can be done with the rate distortion, and then you can say exactly what you want to minimize, right? And then this becomes more specific, the goal. Here the goal is not specific at all. It's just a general statement. If you reduce entropy, you want to reduce entropy. These are the limits what you can do. It's like energy. I don't tell you what to do with energy. I say, well, you can't produce energy out of nothing. Perpetual mobile, perpetual motion is not possible, no matter what you want to do. That's basically what it says. So here is a concrete scenario where you can see the laws of entropy or information preservation or information variance, and we'll look at a very simple task, a super boring task. And the reason for that is, turns out that this is actually exactly where you can see the effects very clearly. So there's this 11 times 11 world, I think this is 21 times 21. There's a center, and this is a chemical substance here, and basically you have an agent that can observe for directions, and it will take a step into the direction that has the highest gradient. So it will basically move towards the center. A few caveats: if two values are the same, it will randomly pick one, and if it gets to the center, it cannot stop, so it will continue wobbling around it. Yeah, so it's never stopping. It's clearly a stochastic process. Let's have a look at what it's doing. So we have our agent here, our Bayesian network. We do not need the memory. It's a purely reactive agent. It observes a sensor state. It takes the corresponding action, and it decides on the corresponding action that takes it. Nothing special here. Okay, so we can now show that in the scenario if you start somewhere in the world, what does it start in the world? You start, say, in an 11 times 11 area in the world. At the end, you end up roughly in the middle. So 11 times 11 is an uncertainty of almost 7 bits. So 128 would be 7 bits. It's slightly less. So it's slightly less than 7 bits. Then these 7 bits will be squeezed out of the system by what the agent does. And we can then show that the mutual information of the sequence of observed sensor states with the initial state, this mutual information converges to the original uncertainty. In fact, it's obligatory if you want to get to the center. So if you want to squeeze out all the entropy of the initial state, you have to actually process this amount of information. Not the whole information at once. This is not required. The sensor doesn't take in more than 2 bits per step at most, because there are only 4 directions. But over the whole time, that's information you need to process. Sometimes it's easy actually to think going all the way back. So if you're in the center, you want to reconstruct where you came from, then you need these 7 bits. You need to make this step, this step, this step, and you can get back to the original step. This is invertible, okay? Because the whole scenario is reversible, so that's why it's possible to do it like that. This is a conservation law. This guarantees that you can do it. To do it, you need this to be guaranteed, basically. Sometimes you are in luck, namely when there is, for example, an attraction force. If you have some magnet that pulls you to the center, your agent might need to process less than that. But we don't look at that too much in detail. I just want to mention this kind of conservation law. It's a law on the level of mathematics. It's not a physical law. It's a property of the mathematics of this dynamics. So the key motto is there is no perpetuum mobile of third kind. Information doesn't come from nowhere. However, while there may be no free lunch, sometimes there's free beer. Although here there is free lunch, so I should be careful what I'm saying. But let me summarize what this information balance sheet story tells us. We have a task invariant in our case that is basically the minimum information required to get to the center. To get to the center, I have to expunge entropy of W0. W0 is the initial distribution over the states. But I'm not required to tell you how I'm going to process it. Is it spread over time, well, over sensors and memory, or through the environment, as you say, writing it down, putting a trail, and other agents, when I tell my PhD students, remind me of our meeting. I'm basically pushing off memory to my students. They have to remember it, or delegate further, or whatever, right? And this is purely entropic. It's indifferent to the task. It happened to be an entropic problem that we had here, but it's task independent. So I'm going now to say, well, how do you actually specify a task? And that is, as I mentioned, basically rate distortion, or essentially it's MDP model plus information. Let's do it. So the standard MDP model, do you all know MDPs, or do you need my explanation? Yeah, all good? All right. So an MDP model, basically standard MDP model says find the best policy, pi star, but doing that does not quantify how expensive it is to actually execute pi star. It has no consideration for that. And the problem is information processing is very expensive in biology. What does it mean it's expensive? Well, if you have neurons, they use a lot of energy. Our brain uses 20% of the metabolism of our whole body. That is a lot. Still not much. It's 20 watts. It's a little bit less than the hydroelectric plants that DeepMind and these companies need to train the network. So I always joke that the lamp that goes off over the inventor's brain and the cartoons needs more energy than the brain that actually had the idea, which is a bit strange.
Not anymore.
Hmm?
Not anymore. LEDs.
Sorry?
LEDs have changed. That's continue.
Yeah, okay, this is unfortunately this joke becomes dated, but I still use it as long as people know these cartoons. Now, basically, what we are going to change, we are going to include energy costs, information costs, in decision making. So we expand the MDP to an IMDP, where I stands for obviously information, and that means that we are now applying the principle of information parsimony. Any decision we make is chosen such to be as cheap as possible under the given constraint at a fixed utility level. So what does it mean? Formally it's a Lagrangian formalism, nothing magic here. What you say, I wrote it as a minimization problem, but you can equally turn it around. It's really exactly the same. I'm trying to maximize the utility average over all the states. The beta is a Lagrangian parameter. If beta is infinite or goes to infinite, what it means, it's really important that it's maximal. Its value is maximal, so it's the optimal case. When beta goes to infinity, it's the optimal case. And only after I maximize the value, I'm allowed to minimize the information. What you get there is the case of optimal policy that minimizes the mutual information that the action needs about the state. And I basically here identify state and sensor because they are both the same. I choose that part of the state I am needing for the action. Did you have a question?
No, I'm just saying this looks like, you know, the rate distortion formalism, right?
It is.
Instead of minimizing over pi, you could minimize over epsilon, like pick an epsilon.
Yes.
That would go, is that right?
It's almost a rate distortion formalism. Completely right. In fact, when we did that, I was wondering if nobody had done that at that time. And it turned out that I thought probably some obscure Russian mathematician has done it in the 50s. Turned out it was, I was almost right. It was a Russian mathematician, but he was not obscure, it was Platonovich. And he did not do it in the 50s, but in the 60s. And he did it only for one step. So he did not do it for a sequential decision problem. In fact, when you do it for a sequential decision problem, it gets a little bit trickier. It's not pure rate distortion. And I'll explain in a second why. When you are really optimal, you can actually transform it to rate distortion. You basically optimize your function, and the optimal value is independent of policy. So you can use that as a distortion function, or the regret essentially. This is not the regret, but you can choose the regret as distortion function, and it's rate distortion, all straight out of the box. However, when pi becomes small, is not optimal, when beta is not infinity, then what happens is you have to make a compromise. And now basically you have moving goalposts. Then the utility function depends on the choice of your suboptimal policy. The suboptimal policy produces a utility function that's not optimal and therefore not invariant to the policy, and then you have to use that to train your rate distortion. So you basically end up getting a double iteration. You basically have to have it converge over one value iteration step, one utility, one blah or motor step, and so on. That happens to converge, although we do not have a good proof for that.
Oh.
Because it's very ugly.
It's still open?
As far as I know, yes.
Wow.
It's not easy to prove. It's very ugly conversions. But it converges. But that's kind of, so that's why it's not naive rate distortion once it's sequential. The other extreme case is beta to zero. Beta to zero means the following: give me a blind policy, a policy that doesn't see anything, but gets me the highest reward I still can get with a blind policy. That's but beta goes to zero. When beta becomes infinitesimal, that's what it is. It means minimize I. That's first priority. Second priority is minimize, optimize the values, and everything in between. Basically, we expect higher utility requires more relevant information, and essentially, so we can look at different goals. Here is a simple grid world with walls. The walls are real. It's not periodic boundary conditions. And do we go to A? Do we go to B? The actions we can pick is north, east, southwest. You get -1 for each step. So basically, it's a distance. It's Manhattan distance is the cost. You get these two curves. So let's look at the two curves. The curve B is the center. So the center is on average 5.5 steps away, so the value is going to be minus 5.5. And this is the value, the expected value, this is exactly 5.5. I'll explain the x-axis in a second. But the y-axis is the value. For the optimal case of A is in the corner, so it's further away. It's minus 10.5. So it's further out. Takes longer to get there. However, when I make the poor agent blind, and I put dirt on its glasses and can take less and less and less information, interesting things happen, and then the information that you need per step goes down. Now notice one thing, I should probably say that first. For the optimal agent in A, you need only 0.2 bits per step to take it. For the agent in the middle, that has to find the middle of the square, you need 1.2 bits per step. And why is that? Well, imagine that I'm losing my wallet here in the corner of the room, of a plaza, big plaza. Pick some big plaza, I don't know, whatever you want. St. Marcus Place in Venice or something. Okay, if you lose it, it's gone, right? The thieves will pick it up. But let's assume it's not stolen. So you lose it in the corner. All you need to know is go to the corner, and basically you have simple actions to get there. But if you lose it in the middle of the plaza, you need to know exactly where it is. So you need to have the exact coordinate to find it. That's basically the intuition. And so it's much more expensive to get to the point in the center, even if the distance itself is cheaper. In other words, from a point of view of an IMDP, these problems are not equivalent. We had problems to get it published in machine learning conferences because they said, no, that's the same problem. No, it's not. Anyway, this is not the whole story. It will get soon even more exciting. So essentially, when you make the agent blind now, you see that the agent still gets a decent reward for the fully blind agent in the case of the corner. What does the agent do? The agent basically picks randomly one of north and east, bumbles into the corner. It can, the walls are not electrified, so he gets just a time penalty for bumping into the walls and slides along the walls into the corner. So on average, it needs 14.5 steps to get to the corner. And that even for a blind agent doesn't need to know where it is. For the center, however, it drops down to some minus 220, which is basically diffusion. It basically does a random walk, and only if it hits the goal, it stops. So it's really, really a big difference once it's not optimal in terms of information, how well it performs. And now I do a twist. This is a twist. I don't know, who of you knows the term embodiment? Few of you. Okay. So embodiment is a topic that people have argued a lot. By the way, your talk is probably, it was in that direction in a way, to some extent. Embodiment is the argument that robots should not be just machines that are controlled from the top down to do the movements, but they should be built in such a way that they take into account that they live in a physical world. And the argument that organisms are therefore much better than robots because they have a body that is already adapted to the physical environment. For example, humans, they can walk, and it's not very, you don't need to think a lot because your body already does much of the movement for you. Right? Lots of the movements are natural as we go. You try to use the physics and the momentum on its own. And the question is, can this be captured? And there are lots of arguments on how to capture it, and there are, I think, two proposals which I feel are quite cool. One is by the group of Mihal I. The other one is this one, and which I show in a very abstract world. Again, our grid world, exactly the same scenarios now, right? So the grid world, you have to find a goal. We forget the goal in the middle, only goal in the corner. The costs are, as before, IMDP, information MDP. And what we are now doing is something very interesting, something that MDP people say, what? That's equivalent. We permute at each location the direction north, east, south, west. Randomly, ahead of the game. They're permuted and then fixed, so they're frozen. It's not like they're permuted every step, they're permuted once at the beginning of the game. Now, from the classical MVP point of view, it doesn't change anything, because MVP has state, and every state has their own actions associated with them. So you can have a state with north, east, south, west, next state with up, down, left and right, next state with red, green, blue, black. You could do that, but in an embodied system that's not quite the case, because in an embodied system you always live, even if I move here, the same have the same nerves. You have basically a local symmetry map about what your brain is trying to do, and it has similar effects, not identical effects, but similar effects in different locations. And so that's what we're going to disrupt. We're taking the directions north, east, south, west, disrupt them at each location, random fixed permutation, and as a traditional MVP you get exactly the same optimal values and exactly the same optimal policy once you undo the permutation. So nothing new in terms of a regular MVP. What happens when it's an IMVP? Well, that's how it looks like. Again, let's look at the optimum. The optimum for both cases, both are A in the corner, should have exactly the same value. Minus 10.5 in the corner in the normal case, untwisted. Minus 10.5, yes, all good. Sanity check has survived. If you check the policies, they're also the same, apart from the permutation, of course. But once you remove the ability of the agent to see exactly where it is, you make the agent blind, you reduce how much information it can use, it gets much worse. So the one with a twisted world, even when it's optimal, it needs much more information about where it is to pick the right action. The one without the twist doesn't. Why is that? Well, it's easy to understand if you remember what we said. What's the optimal action? Basically, most of the time you just have to go north and east. When you hit this wall, okay, you have to go east. When you hit this wall, you have to go north, but that is rarely the case. So most of the time you are somewhere in the middle, north and east, fine. If you have a twisted world, then the problem is that north and east don't always do the same thing. So if I'm here, I want to go this direction, but this one is south, this one is west. Here, oh, this is east, this is west. If I'm here, this is perhaps north, this is west. In other words, I have to know where I am to pick the right actions. That's why I need this information. So what we claim is that the twisted MVP is a way to measure how good your embodiment is. So basically you take your embodiment, or your labeling of your actions, twist them, and then you drop in your quality, and that tells you how much the choice of the right twist gave you in the first place. That is kind of the argument that we have. So in a way you can think of that if you have a well-arranged compass rose, you basically can take this action or this action, all these actions are equivalent. If they're ill-arranged, then I have to know exactly what compass rose I have in every location. So if I just go north, for example, this is how my path could look like. And in fact, going to the goal might look like this: east, north, south, north, north, west. It's very clear there is no structure in this that we can use. We have to really know where we are. And an illustration is if I have a world and I always walk to the north. I always say go north in a world that's twisted to 5%. Basically, most of the time I still go north. If it's 25%, I don't go north a lot, and if it's 100% twisted, I basically don't get very far when I always go north. So you see that having a consistent direction gets me much further. I have much more choice of how far I go without having to think. Anyway, I'll skip that one because I want to move to a different topic. But it's related, and again, Ludwig Wittgenstein has this nice quote. The problems are solved not by giving new information, but by arranging what we have known since long. And here's a nice example of that. I'll start with that one. How much time do I still have, just to make sure? Is that correct?
So I realized you scheduled an hour and a half
Yes.
after having previously, you have plenty of time.
Okay, good. And then we'll have a few more things to say. So here's a nice example that was done by Alexander Klubin, one of my students, and this is an IBO. It's a cute little robot of dog form, and it looks at the Book of Pearl, very fittingly so. And what we took is a quote from Franz Kafka and modified it. There's a famous quote from the Metamorphoses. As one day Gregor Samsa awoke from inquiet dreams, he found himself transformed into a monstrous insect. And we replaced the insect by an IBO. So you're reborn, and with this thingy here, somebody talked about reincarnation. And let's assume what happens is this is your retina, or this is what your brain gets from the retina, and this is your retina. And some nasty evil creature reprogrammed it in complete random fashion. That's not very pleasant. In a way, that's how we are born we don't know exactly what fits what. And so what we did is we looked at a scrambled vision of what the IBO sees. The actual retina is well organized, but it is not something that the receiving part knows. So what it gets these information streams, and we measure the information distance. So there's a way of measuring that. If you're interested, I can go into more detail. And the things that are closer together are grouped together. Things that are further apart in information distance are grouped apart. And this is purely statistical. So they're grouped apart statistically. And then there's an algorithm, that's the part where we assume geometry, where the close-by objects, the close-by channels are grouped together. And so this is the original picture that you see when nothing is scrambled. This is a scrambled picture, and this is the reconstructed one. So let me do that, and I do that by hand because this air mouse is not the most convenient way to run that.
Sorry, what's it a picture of?
This is a picture of something, an environment. Some environment. Right. So.
Oh, okay. It's like a building.
All right. So this is a picture of the environment. The robot walks around. This is a scrambled picture, and this is the reconstructed picture. Okay. You see that it gets the broad outline of the space right. It loses the orientation because it has no idea what's up and what down is. Right? There's no symmetry breaker for that. But it gets the areas more or less right. It's not perfect, but it's quite good for something that has no access to the original picture. And we use this model to, let's see whether I have it. Yes. So you can just now run these streams from all sensors of the IBO, and that's what I'm going to do now. And all the sensors of the IBO, and basically reorganize them by projection into a two-dimensional space. So here it goes. And you can see this is as it's organizing itself. This, you can guess, it's actually the visual field. Right? It's a nice arranged array structure. The system doesn't know anything about that. It just tries to map it into projecting to a two-dimensional field. And you can guess, even if you don't know anything else about this poor animal, you can guess it's actually bilaterally symmetric organism. Just by looking at that, you can already guess.
Is that PCA only?
That is not PCA, it's...
TSNE?
No, I think it was just SME.
Oh.
Probably was just an early version of SME. Right, nothing fancy, right? But you could use any other thing. You could project in 3D. So these are the legs. This is, I forgot what that is. That is obviously doesn't have much effect. It's in the zero. But the forward legs, backward, forward right knee, forward right left, forward left knee, and these things can be nicely separated. Okay. And here I have another one. That is something for our developmental friends. So this is a really interesting one. So here we actually did a very cruel experiment, or at least it's cruel if you do it to animals. So with IBOs, we didn't ask the PETA whether they like it for IBOs. So basically there was a notorious experiment where they took cats, little cats in the developmental phase of their visual field, put them in a cage where there were only vertical bars and let them live there for a long time, and then they were put in a general environment, and these poor animals were not able to see horizontal structures anymore. So basically they lost the ability to actually distinguish that, and we actually recreated that with the IVO. Let me just restart that movie. So I'll start it from scratch. Oh, I have to restart it. For some reason, so here we put the IVO in a world with vertical fields, and you see very nicely how it gets these clusters of things that can distinguish these lines essentially, and everything else is separated, so they cannot actually really compare the further away sets. And as we run that with time, we then put it back into an environment where the lines disappeared. And unlike the poor cats, our IVO was actually able to rebuild its full perceptual structure once it's being put back again into a well-formed environment.
Did the environment change in the middle?
Yes, we modified that. Okay, so now I have various choices of what I can talk about. So one thing is digested information. It's basically information that was regurgitated by others. I will talk about empowerment. I think people will kill me if I don't do that. It's like the gig that you always have to play in a concert. Everybody expects you to, Bohemian Rhapsody or something, whatever. But there are several things I can talk about. Digested information or sensor evolution. What do you prefer?
So what's the second one?
Sensor evolution.
Sensor evolution?
Sensor evolution. Okay, let's move that. So this was basically learning from others. Okay. Yes. Okay, let's go to sensor evolution. So this is something I talk to many people, that's why I'm suggesting it as a topic for today. So we remember this curve, right? This curve was essentially how much value do you get for how much information that you achieve. If you have lots of information you take in, you get more value. At some point it peters off and there's some good balance. And this claim is, the hypothesis is that if you're an organism, you live on the edge, right? Or near the edge. You don't want to be in here. And the reason for that is that if I'm sitting here, it means I'm using a lot of information, cognitive burden, or we don't want cognitive burden. So as evolution wants to push us here, it wants to reduce cognitive burden. Evolution also wants to maximize effectiveness, and you can think of that as like two agents pulling the system in this direction. And as long as you're somewhere in the middle, they work together. One pushes towards less information, and one pushes towards more effectiveness. And so they move somehow to the boundary, and until they reach a boundary, they collaborate. They reach a boundary, it's over. And now they can start competing. And the competition means that if you want more effectiveness, you have to increase the cognitive burden, which you don't like. And if you reduce cognitive burden, you reduce effectiveness. So again, the other drive doesn't like it. And once you are here, therefore you're stuck. So if you want to move to a different niche, it gets a problem. And there's some very interesting effect of this. And one of the things that really struck us is that organisms are super good at extracting a lot of information from the environment. As you mentioned earlier, we can see individual photons. Why would we? We are not nocturnal. Still, we can do that. Why is that? And this is a thing, it's a long story behind that, a thing that really bugged us a lot, and we try to have a model for that. So once you're here, basically, you're in this trade-off scenarios. So we have the sensor-actuator interaction. Actuators are driven to utilize superfluous information. This is a postulate. So if you have information, you want to use it, because otherwise, why have it? Ideally. The sensoric apparatus is driven to minimize consumption. So if you are a cave fish, then the cavefish become blind. They don't have light, they don't need eyes, they forget about eyes. They basically become blind, and that's true. The alternative is, if you're a deep sea fish, there's no light there. What do the deep sea fish do? They make light. So these are the two options. Either forget about your sensors, get rid of the sensor, or make the sensor useful again. Make sensors useful again. It's not a political slogan. So make sensors useful again, and that's what they do. So these are the two options that you have. So there's a sensor actuator arms race here. A sensor that is there allows new behavior. This actuator basically, you have this new behavior, and now when you have new behavior, you might want to adapt your sensor to the new behavior that it fits this. So you have this mutual arms race of things that happen in the same organism in a way, the same species, but it's still an arms race. And the Pareto dilemma is that we already talked about that. So below the trade-off curve, it's cooperation. At the trade-off curve, it's antagonistic. And now the problem is any further adaptation or optimization requires both to collaborate. And strangely enough, that seems to happen more often than not. Why? Well, I want to give first of all examples for that, right? I make statements, but here are examples for exaptation between niches. What is exaptation? Is lateral evolution or lateral adaptation. You are specialized in something and then you become specialist in something else. So lung-based hearing of amphibians. So amphibians that can actually hear with their lungs. And no reason to laugh. You go to a loud discotheque, people want to hear the boxes in their belly, right? So it's similar in a way. Infrared sense of the rattlesnakes, I mentioned that to some of you. It's actually the same hardware that we have in our trigeminal nerve. The rattlesnake is a vertebrate hardware, and the rattlesnake evolved a way to use it as an infrared sensor. It is mainly mechanical evolution. So it's not even that the hardware, the nerve hardware changed a lot, it's just how it's organized in the skin. That's very striking. It's essentially, we could do that, we could have a very special operation to make it look like that, we could actually see infrared. And not a good idea, it's very complicated and creates ugly holes in the face, but never. Near-optimal sensors, individual photons. These are total receptors. This statement is old. Today we know even humans can do that. Humans can identify individual photons. The inner ear can detect force differences that are close to the thermal noise limit, at least for small children. Right? Once you go to a disco, it's over. But small children basically can pick up physical pressure information at the limit of noise. So obviously, nature is really optimizing it to the limit. And the question is, how can we move along the Pareto surface from one niche to another? And how do we drive sensors to the physical limits? So here's the model that we used. And it's based on relevant information, what I mentioned before. It's related to this optimization of information and information you need. For this, we use the information bottleneck formalism. So let's look at the core relevant information. What's the core relevant information? Core relevant information is the information you need to perform optimally. I'm only looking at optimal performance now, right? Optimal performance, I have certain distribution of actions given the world, and that gives me core relevant information. This is the true information I need to make my best decisions. And now I'm looking for, give me a sensor that captures this relevant information. So I have the world, I have a sensor, I have the actuator, and the sensor should be optimal. It should be as good as it gets for that type of question. And I demand that the information that the sensor gives me about the actions is the same as the world. It's basically a sufficient statistics. Does it make sense? Secondly, I want the information that the sensors take about the world to be minimal, because I do not want to use more information than necessary. It's expensive. Remember, information processing is expensive. So, this is how it looks like. We have a navigation task. There's a goal here. There's some obstacles here. There's the critter here. And we take an information optimal policy. and the optimal sensor looks like that. All sensor means it basically classifies different locations in the world, right? There is no vision sensor, it's just an abstract sensor that looks at the world and can distinguish different states. So all these states are one state, all these states are another, and so on. This is information optimal for this goal. Now, we can ask the following question. The evolutionary question now says, oh, we're not happy just with one goal. What other goals can I do? What else can I do with an already existing sensor? What other things can I eat? And we now can ask, okay, what other goals are supported? And when we do that, forget the dashed curves, let's just look at the solid one. When I organize the tasks by quality, this is the highest good. So I wanted tasks at the highest level. I organize them by quality. Then basically the few less qualitative, less high tasks are nearly as good as the best tasks. So if I look at alternative tasks, apart from my main task, they're not losing much. I can basically get a lot of good tasks with my sensors, not just the original one. Yes?
So what do you mean by quality tasks?
Quality, there's a value for the task. Every step costs me a unit. So the cost of it, how much reward do I get for the task? The best task that I have gets to give me reward -2, and basically the next best tasks are not much worse. And they are supported by the same sensor. I will accept any adaptation that is at 95% performance. So I am allowing to evolve sideways to any task that's not worse than 95% of the original task. If I do that, I see that the world is almost fully connected. It's very easy to get from any goal to any other goal. These are all the goals that are possible in the world. It's a small world. By just an adaptation that costs me only 95%, I adapt and then I move again. So essentially this graph connects two nodes. Basically each node is a goal. It connects two goals. If the optimal sensor for that goal is good enough for the other goal to be reachable at 95%. So then I connect them by an edge.
I need to restart the recording, so you're going to lose a couple minutes. Just FYI.
Yeah, I can.